Hello everybody, this is week 8 of Roadmap to Web3 and today we are going to talk about two separate topics. One of them is going to be optimism and the optimistic rollups. The other one is going to be randomness. We are going to finish this by making a betting game. So, who am I? I'm Ori. I'm a content developer at OP Labs, which makes the Optimism rollup for the Optimism Foundation. And if you need to email me, here's my email address. So, what are we going to talk about? We are going to start with why do we even need rollups? Isn't Ethereum complicated enough? Then we'll talk about how do rollups work and how to use rollups. We'll then build a sample application, a betting game, and that sample application is going to run on the Optimism rollup. In fact, we are going to run it not just on Optimism testnet, but on an Optimism mainnet to show you how cheap that is. Then there's an exercise for you to modify that game and questions that you should discuss, think about, etc. Why rollup? Optimism is a great system, but it may not scale enough. If we want to get the next billion people, we can't have high transaction costs. Ethereum has limited capacity, and therefore we have congestion. And since gas costs are essentially an auction for block space, we are going to have high gas costs and price people out of the market. Why do we have this limited capacity? Why can't we just say, okay, instead of a target block size of 15 million gas, let's do 15 billion gas? The reason is that every transaction needs to be executed by thousands of computers, and even after the merge, it's going to be 100. We could achieve this by being centralized, by making it so only very rich organizations can run nodes. But that's not the point. If we want to do that, why do a blockchain at all? To be truly decentralized, we need the average person to be able to buy average hardware and use that to run a node. So how do we reduce the load? One way is to use L1 just as a dispute resolution mechanism. Imagine, for example, checks. I give you a check. Do you go to court to cash that check? Of course not. You go to the bank, you try to cash the check. If the check goes bouncy, 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 then you go to court. Now, the very fact that you could go to court, get the money from me, and give a big hit to my reputation is motivation for me to make sure that the check does not bounce. But you don't use the courts unless there's a dispute, and we want to use L1 pretty much in the same way. How do we do it? We do rollups. We roll all the transactions up and write them to L1. Now this means that we inherit the L1 guarantees of availability and integrity. However, we can calculate the results of the transaction elsewhere on our own system for cheap. Now the problem with this is, hey, so our calculation is centralized. I can see the transactions, but why should I trust you that you calculated them correctly? The answer in all types of rollups is that we need a mechanism to ensure the reported results are accurate. We'll start with zero knowledge rollups, which I don't know all that well. We're the other type, optimistic rollups, so take what I'm saying with a grain of salt. You calculate a zero knowledge proof, which is expensive for the state transition, but now the proof is going to be verified on L1, and verifying a zero knowledge rollup is cheap. What's wrong with them? Why do we even need a different solution? This looks ideal. Well, they rely on very complicated math. It may or may not be possible to run the EVM on top of a zero-knowledge rollup. Now, when I say that, the zero-knowledge people can start yelling at me, yes, Ori, you say that, but we already proved that zero-knowledge is Turing complete. This means that you can run anything on it, specifically the EVM. Yes, but Turing complete only tells you that something is theoretically possible. It doesn't tell you if you can do if the performance is going to be good enough. So being Turing complete in and of itself doesn't prove to us if we can practically run the EVM. And also, another issue is that it is difficult to find people to audit the code. The world has thousands or tens of thousands of EVM programmers. I don't know how many people know zero knowledge, but I expect the number of people who are good enough that they can review the code and find various complicated bugs is in the hundreds. So what's the other solution? Optimistic rollups, like what Optimism does and like what Arbitrum, our number one competitor, does. This means that we post the results on L1 immediately and we post the Merkle root of the result. We don't post the entire state. And there is a fault challenge window for others to dispute them. This means that instead of relying on math, we are relying on economic incentives. If you're the sequencer and you post the correct result, you get rewarded. If you're a verifier and you dispute an incorrect result, you get rewarded. But both sequencers and verifiers have to post a bond, because if they post an incorrect result or dispute a correct result, they get slashed and they lose a significant amount of ETH. This whole thing is based on fault challenges. What are fault challenges? They are originally called fraud challenges. The name has been changed to avoid drawing regulatory attention. Imagine a regulator sitting in a building somewhere in DC. The moment they hear the word fraud, their ears perk up, their eyes open, and they are very, very interested. We don't really need to want that. We want them to just let us do our work. We'll make sure that we're honest. So we call it fault challenges. The stages of how do we do them is first we do bisection by step, and then we execute a single step on L1. So what does bisection by step mean? Let's look here. The proposer statements are going to be in orange, the challenger statements in blue. And before we even start the transaction, both of them agree that it's S0. Then the proposer says, oh, after the transaction, the state is S7. The challenger says, S7? Are you crazy? It's S7 tag, it's completely different. And the L1 contract says, okay, if the two of you think that it's different, why don't you tell me what it looks like in the middle after step 4? The orange says, well, after step 4 it's S4, of course. The challenger, S4? It's S4 tag, you crazy person. The L1 contract says, okay, so whatever is your disagreement, it happened before S4. I get it. Now, what's the situation about after S2? The proposer says, after step 2, it was S2, duh. And the challenger says, finally, you're saying the truth. After step 2, it was S2, you're right. Okay, so now the challenger, the contract, and everybody else knows that the problem is either with step 3 or with step 4. The contract then asks them, okay, you people, what about S3? What is the difference with the state after S3? The proposer says, it's S3. The challenger says, you're back to your old tricks. It's S3 tag. So now we know that since they agree on the state after step 2, they don't agree on the step after step 3, the problem must be in step 3, and we are going to execute this step on L1. How do we do it? In the case of Arbitrum, you transpile EVM to AVM and you execute one AVM step. In the case of Optimism, we're not quite there yet, but the system we are working on compiles geth to MIPS and then runs the MIPS geth on the EVM. So essentially we have an EVM running on top of geth, running on top of EVM, running on top of geth. This means that the performance will be very, very bad. But it's okay because we only need to run a single MIPS opcode to see whether the proposer is right and the state is S3, or whether the challenger is right and the state is S3 tag. One opcode, it won't take that long, and Arbitrum is currently working on a similar system called Nitro. To put it all together, all the transactions are written to L1, and anybody can verify the state of the blockchain at any point. The state commitments is probably accurate because as long as there is one honest verifier that can challenge it, it will become the connect value, and the economic incentives are aligned with honesty. Basically, we don't assume that people are honest, we assume people are greedy, and then we make it so that if you're greedy and you're honest, you get what you want. If you're greedy and you're dishonest, you lose money. This is mostly implemented in a piece of software called the sequencer. It can receive transactions directly at an RPC endpoint, or it can receive them from L1, which is slower and more expensive. But it's necessary because it's uncensorable. You send a transaction to us right now. On RPC, we can say we got it, we can say we didn't get it. Do you trust us? But if you post it on L1, then everybody in the world knows that we got it, and we have to, within a certain amount of time, put it on the blockchain. Otherwise, the Optimism blockchain can't continue. The sequencer decides on the order of transaction, and once we are decentralized, we're not there yet. Before we can decentralize, we need the fault proofs. But once we get there, maybe we'll decide on who is the sequencer by an auction mechanism. This means that we are taking the MEV, the miner extracted value, and we use that, the ability to make money from ordering transactions, to pay for network expenses. Bridges. People already have assets on Ethereum and they want to do transactions. The entities you use to transfer those assets are called bridges, and there are two types, trustless and trusted. Trustless deposit. Trustless is we make a trustless bridge and you can use it on L1. You can transfer between L1 and L2. The user can send assets. Assets in this case are ETH and ERC20, although there is work being done on a bridge for NFT to the bridge on L1. For ERC20 you use allowances, of course, you don't send it directly, and then call the L1 bridge to say, hey, I want these assets on L1 too. The L1 bridge then holds the assets, and sends a message, hey, bridge end on L2, can you please mint those assets for this user? And the L2 bridge mints the equivalent assets on L2. Those assets spend time in Optimism, they change hands, stuff happens, eventually they're owned by someone who wants them back on L1. So the user is going to call the L2 bridge, and the L2 bridge then does two things. First, it lights up a match and it burns the assets. Second, it sends a message to the L1 bridge to say, okay, the assets have been burned on L2, you can release them on L1. Time passes. Specifically, the fault challenge window on our production system, this is currently 1 week. This is considered to be enough time that if there's a problem, someone will challenge it. The user then sends a claim transaction on L1 that includes a Merkle proof of, yes, I really did send this to L2, the L2 bridge really did burn the assets, the message is really there, and then the L1 bridge releases the L1 asset back to the user. This looks a bit complicated and therefore expensive in terms of gas, and slow, especially because of the fault challenge window. That's why there are also trusted bridges, where the user just sends assets to one layer, the bridge then communicates by its own methods and sends assets back to the other layer minus a fee. It is called trusted because you have to trust the bridge to be honest. And how does the bridge do it? The bridge may have liquidity providers, and those liquidity providers provide assets on a certain layer, and then, by the way, the reason I say a certain layer is that it usually has L1 and multiple L2s, and essentially those liquidity providers provide you with a loan until they can get the assets back. And the trustless bridge can then balance out the assets to make sure that there are enough assets everywhere and people can continue to use the trusted bridge. Okay, now it's time for our first demo. How do I use Optimism? I already have an Alchemy account that I use. By the way, this is the free account because I want to verify that everything I do can be done with a free account, since what I do is mostly right education. We will call it Week 8 or Road to Web3 Week 8. Chain Optimism, and we can do the testnet, but we're going to use the mainnet. Create app, and here we can view the key. This is our endpoint. The next step to be able to do anything with Optimism is we need ETH. So let's go here. Let's go to the Optimism app to bridge ourselves some ETH. I happen to already have some. Let's assume that I don't. In MetaMask, I'm going to select Ethereum mainnet because I'm moving from Ethereum mainnet. And I have 0.06. Let's try to move 0.06 and some of it will also be used as the gas fee. Deposit. It takes about 1 to 2 minutes. We are using the trusted bridge. Confirm it in the confirm it in the wallet, of course. We can't do anything on an app without permitting it. Wait about a minute. Okay, deposit complete. If you don't have Optimism on your wallet, you can add it through here. But I already have it, so I'm just switching. And now I can explore apps on Optimism, but what I really want to see is that the money made it, so let's go to MetaMask, Optimism Network, And here we see the 0.06 ETH plus whatever ETH I had before that. Now that we're on Optimism and we have some ETH to play with, let's see what we can do. Ecosystem. Here we see a bunch of DeFi protocols. We have multiple bridges. Let me show you one of them just to show you that you can go to other Web3s, to other L2s also. Let's take, for example, Hop Exchange. And do we allow it to connect with us? Yes. This doesn't do any transaction, it only shows. And let's say that we want to send ETH from Optimism. We can send to Polygon, Gnosis, Arbitrum, etc. And let's see, if we wanted to send some to Arbitrum, how much would it cost us? 0.0004 ETH. Not a lot. Okay, but let's look at NFTs, they're cuter. Quixotic is the main NFT market. And let's see what here looks good. Let's see if we can get a giraffe. And yes, we can. Mint for this amount. Let's connect a wallet. Mint. And this is the price of the minting plus the gas fee. Confirm. Okay, the giraffe has been minted, and let's look at it in Etherscan. So we're going here to account 1. We are copying it. Now let's go to Optimistic Etherscan.io. And we see here that we did something 44 seconds ago. We called mint item, and we see that we got an optimistic giraffe. Now let's go to Quixotic and see if we can see the giraffe there. My NFTs, and here we go. Giraffe, but yak, it is smoking. Okay, now that we've used Optimism, let's make something on it. And our sample app is going to be a betting game. Now, why a betting game? Because we need a random number generator. And the same techniques can be used for NFTs with variable attributes, like the giraffe we've just seen, or the bunnies that we can see here. There is an optimistic bunny project too. Problem: there are no secrets on the blockchain. Everybody needs to be able to verify the blockchain's integrity. Therefore, everything on the blockchain is open. Even if you write private on a variable in your Solidity, it just means it's not available to other contracts on the blockchain. Nodes have to know it as part of their state, so you cannot rely on the secrecy of that either. What is the solution? There are no secrets on the blockchain. You could use a secret as long as it is stored elsewhere. Here's an example. I generate a random number A, you generate a random number B, we add them up. Is it going to be an even number? Is it going to be an odd number? Neither of us knows in advance. So this is our first protocol. Side A invents random A, side B invents random B, side A then posts random A, side B posts random B, and we add them, or we do an exclusive OR on them. I prefer an exclusive OR, but that's just a matter of taste. And this protocol is terrible. Why? Side A publishes a random number. Side B can then choose the random number that would make it win. For example, imagine that even numbers mean that A wins, odd numbers mean that B wins. For example, Side A says my random number is 6, which is 0110. Side B says, oh, good, my random number is 1, which is 0001. The XOR of them is 0111. B wins. Side A cannot tell you what is random A too far in advance, because then B wins automatically. The answer is commitments. Side A is going to calculate a cryptographic checksum of random A, let's call it hash A, and publish that on the blockchain. Now side B can publish random B. Side A, now that B value is known, can publish random A. We can check that the hash of random A is equal to hash A. If they are not equal, something is wrong, A is cheating. If they are equal, we do the XOR and we now have our random number. What's the problem? It can still be abused, this time by side A. Why? As soon as side B publishes random B, side A knows random A, knows random B, and knows the result and can have it affect his behavior. He can't give you a wrong random A because he's already committed with hash A, but there are other things he can do. For example, imagine that side A is spiteful. There's no way for side A to win. But what if he doesn't reveal random A? In that case, side B doesn't win either. The solution to that is actually pretty simple. You let side B have a claim transaction, so if side A takes too long to respond with random A, side B can claim anyway, and we assume that if side A doesn't respond, then side A is still losing. Another more serious problem is front running. What happens is that Ethereum transactions are posted to a public mempool before they actually happen, before they go in a block. Side A can see random B before the transaction, and then side A can submit a transaction with a different random number, but with a much higher priority fee. So a miner will think, do I want the transaction from side B that would pay me this much, or the transaction from it's side A, but he pretends to be something else, that would pay me this much? I know, side A, that transaction happens first, and side A wins. This is more difficult to prevent. Here's how we do it. Side A is going to get random A, publish hash A. Side B is going to come up with random B and calculate hash B. Side A provides a hash. Side B also provides a hash. Now, both of them give the random numbers. They give them at the same time or in any order, it doesn't matter, because side A and side B are both committed. We already know who side B is because of the commitment, so nobody else can front run it. We check if random A is equal to the hash of A. If not, A is cheating, B wins. We check if random B is equal to hash B. If not, B is cheating, A wins. And then we do XOR of those things. Okay, now for the exercise, I'm going to show you how to do the betting game with protocol number 2. If you look in this if you open this QR, it is the repository that contains the actual code. Okay, now let's actually do it. We see here that it's not its own repository. Instead, it's part of the kobzut.github.io repository, and it's /logrocket, which is a blog in which I publish articles. For example, I published there one that explained randomness. So let's go here, code, copy the URL, and now let's clone the repository. Git clone URL kbzt logrocket 2206, and now we can open Visual Studio and see this is the casino.sol with proposed bets and accepted bets. And if we want to actually test it, here is casino.test. We want though to play with the contract manually to get a feel for what's up. To do that, let's go to hard.config.js. You see here we use .env for the information that we want to keep a secret. Let's remove the two networks here that we don't need, and Optimi and the URL, instead of using the rate limited endpoint that Optimism provides, let's use one from Alchemy. Okay, so now we'll create the .env file. URL is going to be our Alchemy endpoint that we created earlier, which is this one. Copy. And the mnemonic is going to be... Come on, you really think I'd fall for that? I'm not going to tell you what my mnemonic is. Okay, now let's do yarn to install all of the packages we need. Okay, now let's do yarn hard hat console network optimism. Okay, I want to show you how much things cost, and this gives us the initial cost. Now let's deploy the casino. So factory is equal ethers get contract factory casino. Well, factory is equal to await factory, and now contract or casino is equal to a factory deploy. Okay, first I want to see how much it cost. So let's get balance 1, our current balance after we've spent this. And now let's do balance 0 minus balance 1 to get the cost. And yes, this looks like a large number, but this is because it's a number of way. Way are very, very small in value. If you look at it as Optimi at ETH, this is the number. As I'm writing this, ETH is worth about 1,500, so it's still less than $3. Not too bad. Okay, now let's start playing with it. But to play with it, we need to first know a few things. We need to have values and hash to send. Here. The reason that for val A and val B I used SHA also is to create a value that is 32 bytes long. Because if I calculate ethers, utils, hash of, let's say, 0, 1 byte, and hash of 0, 2 bytes, you see those are different values. And I need a 32 byte value, so I could either type 64 zeros or cheat. I cheated here. Now let's see, how do we propose a bet? We just call the contract with propose bet hash A. So let's do that. tx1 is equal to await ethers. Sorry. Casino dot propose bet hash A. Now I'm already going to tell you, spoiler alert, this is going to fail. And it's going to claim that it fails on being unable to figure the gas. Let's give it an amount of gas just so that won't be the issue. Optimistic.etherscan.io. This is the contract address. Here we see that it failed. And if we look here, we can see the reason. You need to actually bet something. We forgot to send ETH with our gamble. So let's do that. Instead of putting here a gas limit, let's do value. And let's gamble 1 GWay, 1 gigaway. Okay, now let's look at this one. Also in Etherscan, so we'll go back to the contract. And this is the successful proposed bet. We can see here that there's a log of bet proposed. This topic is the commitment. And here we have, and here we have the value being proposed, the value of the bet. Now let's accept this bet. How do I do that? Let's look here. To accept a bet, you need to give it the hash of the proposed bet, your random number as B. Remember, we are doing protocol number 2 here, not protocol number 3. That's your job. And of course, you need the value, you need to send ETH that you're going to gamble. So, tx2 is equal casino.acceptBet hash A val B win, and we need to override the value, which is 0 by default, and put here the same amount, in this case 1 GWay. And of course it's a promise, so let's wait for it. And to get the receipt, we are going to again await tx2 wait. Okay, or we can also see it here. Let's go back to the address that emitted it, and here we see a successful accept bet from the same address, because we did everything from the same address. And here we can see things. And now let's try to settle the bet. So tx3 is await casino reveal. And in the reveal, we're just going to have to put val A. We don't need to actually give it the hash because it can calculate that on its own. And here it shows us that the bet was settled. And if we look at the logs, we see that the bet was settled. We see who was the winner, who was the loser, and the value. And your exercise is to upgrade this betting game from protocol 2 to protocol 3 to prevent front running. Also, some questions to think about. When I want to bet, I don't feel like waiting until somebody else takes my bet. Can we do betting between a smart contract and an externally owned account? If you can do it, how? And if you can't, why not? Question 2. You don't want to send larger transactions. When you use a rollup like Optimism, the actual cost of running the transaction on L2 is usually negligible. The real cost is the cost of writing the transaction to L1. You don't want to increase that. How can you do this? Can you do this? If you can do it, how? And again, if you can't do it, why not? Question 3, you want to shuffle cards for an on-chain game of poker. Now, part of the point of the way you play poker is that players know their own cards, they do not know the cards that other players have. Is there any way to do this on-chain? If so, how? And if not, why couldn't you? And this is the end of the lecture. Thank you very much. You've been a great audience. I hope you enjoyed it.